Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video, I am reading chapter Chemistry of Actinides of Inorganic Chemistry. Actinides constitute a series of elements following actinium atomic number 89. In the seventh period of the periodic table, actinides belong to F block as these are formed by a gradual filling of 5F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides, which follow lanthanum, involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. This series of 14 elements is called the actinides. Actinides, along with lanthanides, constitute for complete F block elements. The ending "ide" in actinides is not appropriate because it more correctly means negative ions such as oxide or chloride. Actinides were also named actinides by a group of scientists. However, the ending "on" is used preferably for non-metals such as boron, silicon, etc. Whereas all the actinides are distinctly metallic, IUPAC has now recommended these elements to be called actinoids with the ending "oid" rather than being called actinides or actinides. However, if it is unfortunate that people still call these elements by their earlier name as actinides, before World War II, the only naturally occurring actinides, namely thorium, proactinium, uranium, were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. These elements are named man-made or synthetic elements. Another name coined for these elements in transuranic elements. Transuranic elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspects of the chemistry of actinides. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas radon as: after radon, the 7s and 7p orbitals gain stability relative to 5f orbital because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new elements francinium and radium belonging to s block of elements. After the radiation of two electrons in the radon core, the 5f and 6d electron penetrate the 7s orbital. The least penetrating f orbital are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium to leveryanisium enter the 5f shell. It is important to note that around actinium, both the 5f and 6d subshell possesses almost similar energies. Because of similar energies of 5f and 6d subshells, the incoming electron may enter either of the two subshells, which results in the uncertainties of the electronic configuration. As a result, it is doubtful whether the electron enters the 5f orbital or not. For example, the configuration of thorium may be written as, look at this. However, once filling start in f orbital, the f subshell becomes more stable. As a result, from uranium onward, the f5 cell becomes more stable, as shown in figure. Thus, all the incoming electrons start filling progressively in f orbitals. The general electronic configuration of actinides can be assigned. General characteristics of actinides. Some of the general characteristics of actinides are detailed below. Electronic configuration. As a result, discussed in section 5.1, the actinides involve the gradual filling of 5f subshell. The electronic configuration of the titled actinium. Thus, from thorium onward, the 5 subshell starts progressively filled. The general electronic configuration of the atoms of the actinides in the ground state may be written as: melting and boiling points. The melting and boiling points of actinides are moderately high but are lower than those of the transition elements. An inspection of the table 5.2 reveals that there is no regular trend in the melting and boiling point of the known actinides. Density. An inspection of the table 5.2 reveals that the elements near uranium have very high density. American resembles the corresponding lanthanide europium in being less than its neighbors. Ionic radii and actinide concentration. The size of the actinide ions decreases along the actinide series. This is with increasing atomic number. The extrancing on the nucleus is poorly screened by the electrons. This steady decrease in ionic with the increase in atomic number in actinide contraction. A comparison of M3 positive ion radii off with those of the lanthanides reveal the actinide and lanthanide ions vary in size. As a result, their chemical properties are also similar. The decrease in the ionic ions in case of actinides. But interesting to note that there is a decrease in the atomic radii from thorium to uranium, which may be increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from the uranium may be considered to consist of Mn positive ions with a total of N electrons for atoms. After the metallic radius increases significantly again, which may reflect the increasingly lanthanide-like oxidation state. The actinide elements show a greater range of oxidation states than the lanthanides, particularly in the early part of the series. The different oxidation states of actinide elements are shown in the table 5.3. Bold NOS are most common oxidation state. The oxidation state shown in parentheses are unstable. The +2 oxidation state in case of actinides is very rare. Am2 positive has the electronic configuration. It is analog of Eu2 positive in the lanthanides but exists only in the solid state as the fluoride. AmF2, on the other hand, exists as ions in solution. The properties of divalent actinides resembles more closely to Ba positive. In group 2, the more stable +2 oxidation state is exhibited by nobelium and corresponds to stable 5F14 arrangement. The +3 oxidation state is the most common oxidation state along all the actinides. However, this is not always the most stable oxidation state in the actinides. The first four elements show +3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized in air as well as in the solution. Interestingly, the most stable oxidation state of elements up to uranium is the one involving all the valence electrons. Thus, the most stable oxidation states respectively. Although neptunium shows the oxidation state by involving all its valence electrons, it is not the most stable state. This is because an +7 oxidation state is highly oxidizing and the most stable. One of the most commonly encountered compounds of uranium oxidation state is uranyl nitrate dihydrate. It consists of linear ions surrounded by two NO3 negative ions and water molecules as shown. The NO3 negative groups are bident and therefore two oxygen from each NO3 are bonded to. Uranium oxygen atoms from the two water molecules also bond to uranium. Thus, the coordination number of around uranium is 8. The UO2 positive in the compound is perpendicular to a hexagon of 6 oxygen atoms formed by Gint NO3 group and 2 form water molecules. The lower oxidation states are ionic, while the higher oxidation states are increasingly covalent. Co-oxidation state is known only in the oxocations of and when alkaline solution are oxidized by O3. The important oxo anions known in case of NP and PU are color of the ions. Actinides ions are mostly colored. The color of a particular actinide ion depends upon the number of electrons present in the 5F orbital. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cations formed by the actinides ions in aqueous solution are given in table 5.4. In addition to FF transition in actinides, the color can also arise due to FT transition as well as charge transfer transitions. The color of the actinides ion solution because of FF transition occurs in the visible and ultraviolet regions. We have already encountered these FF type of transitions in case of lanthanides as well. Since the 5F electrons in case of actinides are projected out more in space than the 4F electrons in the lanthanide, these 5F electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterize easily. It has been experimentally found that the absorptions due to FF transitions in case of actinides are nearly 10 times stronger and 2 times broader than the FF transitions of lanthanide ions. The energy difference between F5F and 6D orbitals in case of actinides being smaller than 4F and 5D orbitals in case of lanthanides. The actinide ions variously absorb light of lower frequency. As a result, the allowed and very strong FD transitions lie in the ultraviolet region and therefore do not influence the color of the actinide ions. It has been observed that the actinide ions in higher oxidation state display predominantly charge transfer spectra. This spectra is exhibited only by high oxidation state ions which can easily oxidize the ligands. Do not display oxidation states higher than 4. Magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic moments with the number of unpaired electrons. This is shown clearly in the figure 5.4 where the magnetic moments. This is due to the fact that 5f electrons in actinides are projected more in space to the crystal field. As a result, the partial quenching of orbitals occur by the crystal field effects. Reactivity. The actinides are highly reactive metals. These react with dihydrogen and form known stoichiometry hydrides with the formula MH2 or MH3. They react with hot water and tarnish in air, forming an oxide coating. The actinides react readily with HCl, but reactions with other acids is slower than expected. The metals are basic and do not react with sodium hydroxides. The actinides react directly with the halogens to form a variety of halides. The redox potentials for the known M3 positive M couples 8 about. Thorium and uranium chemistry has been explored in detail. Some of the general methods for preparing compounds for chemistry of separation of neptunium, plutonium, and americium and uranium. The three elements neptunium, plutonium, americium that follow uranium is the actinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the oldest known element amongst the actinides. Naturally occurring uranium contains two main isotopes, neptunium and plutonium, named after the planets Neptune and Pluto, were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutrons in the cyclotron in Berkeley, USA. Both the elements are now obtained from spent uranium fuel elements of nuclear reactors when they are formed by the capture of neutrons produced in the fission. Isotopes of plutonium Pu can also be prepared by reaction in which fast neutron is added with the subsequent loss of two neutrons without allowing time for the intermediate products to decay. Americium can be obtained from the isotopes of plutonium by the success reactions in the nuclear reactor. The yields of the heavier elements after americium is controlled by two factors: the half-lives of the various isotopes by their ability to absorb neutrons. It is important to note that the stepwise addition of slow neutrons is very difficult. A quick method is to bombard the nucleus with a large number of fast neutrons without allowing time for the intermediate product to decay. For example, adds a fast neutron and then loses two neutrons to form an isotope of neptunium according to the reaction. The separation of these elements from uranium is extremely difficult and hazardous. It is because these elements, including the starting material, are not only highly radioactive but also give highly radioactive fission products. Plutonium especially is extremely toxic. The separation of NP, Pu and Am from U are based on the following chemistry. Stability of oxidation states. A steady decrease in the stability of high oxidation states with the increase in atomic number have been observed. With the increase in the atomic number, the order of stabilities of the major ions involved are: separation of these elements from uranium from which they are obtained in the nuclear reactor from fission products and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential and then using solvent extraction or precipitation. For example, Pu can be oxidized while Am remains as Am3 positive. Thus, plutonium Pu can be removed by solvent extraction, whereas americium can be precipitated as AmF3. Extraction into organic solvents. The MO2 positive ions from solutions can be extracted into organic solvents. The M4 ions are extracted into tributyl phosphate in kerosene from 6MHNO3 solution, whereas ions are extracted from 1016MHNO3. Precipitation reactions. Actinides in the +3 and +4 oxidation states can be precipitated as their fluorides or phosphates from acid solutions. The higher oxidation states beyond +4 give either no precipitate or can be prevented from precipitation by complex formation with sulfate ions. Ion exchange methods. Ion exchange methods are commonly used in separation for small amount of materials, as in the separation of americium. Spent uranium fuel rods removed from the nuclear reactors can be used to extract NP and PU in kilogram quantities, where AM in 100-gram quantities. The repurposing of nuclear fuel rods is an important technology, as this helps to extract new elements that may be used as nuclear fuel. Spent fuel rods are dipped in ponds of water for several days to allow them to cool. During this dipping period, the intensity radioactive isotopes with short half-lives such as lose most of their activity. The fuel rods are dissolved in 7-MHNO3 and extracted with 30% tributyl phosphate in kerosene. The extraction coefficients of the actinides in 7NHO3 solution containing 30% tributyl phosphate in kerosene are. As a result, nitrates of uranium and are preferably extracted in tributyl phosphate, leaving the other actinides, namely NP and AM, along with other fission products in aqueous solution. It is also important to note that 7NHNO3 can not oxidize to higher oxidation states. Uranium species present in kerosene oil on treatment with 0.2 NH-NO3 gives UO2-NO3 square in aqueous solution, which on evaporating leaves a solid mess of composition. On heating this hydrated solid compound to 400 Celsius gives UO3, which upon further reduction yields to UO2. On the other hand, aqueous solution of reduced PU solution on treatment with nitrous acid gets oxidized to PU. This solution reacts with oxalic acid to give crystalline precipitates of the composition. Heating the hydrated compound to 300 Celsius gives PuO2. The whole sequence of steps outlined in the process are described in figure 5.6. The separation of other actinides, namely NP and AM, can be achieved by the use of appropriate oxidation reduction cycles coupled with solvent extraction. For example, PU3 positive in aqueous nitric acid can be oxidized by an oxidizing couple followed by extraction into hexane, whereas AM3 positive is unchanged and remains in aqueous solution. Transuranic elements. Elements with an atomic number greater than 92 are called transuranic elements. Before the Second World War, the elements thorium, proactinium, and uranium were located below hafnium, tantalum, and tungsten in the periodic table. The synthesis of neptunium, a new element with atomic number 93 by M.C. Millen and Abelson in 1940, was demonstrated by bombarding uranium with neutrons. This newly discovered element should be positioned immediately to the right of the tungsten below rhenium. The properties of neptunium resembled more with uranium than the rhenium. It was the discovery of neptunium followed by the subsequent synthesis of new elements that were responsible for the new senses of elements called the actinide series. All the transuranic elements are radioactive in nature and have short life period. Neptunium, plutonium, and americium were known prior to the synthetic preparation via nuclear reactions. However, these elements were later found to be present in trace quantities in uranium ores. Synthetic routes to transuranic elements. There are two synthetic routes which are commonly used for the synthesis of transuranic elements. A neutron may be captured by the nucleus with the emission of gamma rays reaction. The neutron increases the mass number of the nucleus by 1 unit and some energy is released and gamma radiation. Further neutrons may be added in a similar way. Addition of neutrons increase the neutron to proton ratio. This makes the nucleus unstable because it contains too many neutrons. As a result, the nuclei decay by converting a neutron into a proton and a beta particle. This reduces the NP ratio and also increases the atomic number by 1. Thus, a new element is formed. The other method involves the capture of small ions by the heavy nucleus. This is possible only if the bombarding particles have sufficient energy to overcome the Coulombic repulsions between the ion and the heavy nucleus. The smaller ions are accelerated in a linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ion used in the alpha particle. This increases the atomic mass unit by several units and the atomic number by 2 units. Actinides with atomic number 93 to 102, californium to nobelium, also display +2 oxidation state except for nobelium. +2 oxidation state is strongly reducing in nature. Higher oxidation state of curium are found in the solid state in compounds such as CM4 and RbCmF5. Similarly, berkelium compounds are stable in the +4 oxidation state such as BKO2 and CS2. Lawrencium exists only in the +3 oxidation state and resists oxidation and reduction. This resistance to oxidation and reduction illustrates the stability of an F14 electronic configuration ion. The elements up to atomic number 100 undergo radioactive decay mainly by emitting alpha particles or beta particles. The later elements become increasingly unstable as the atomic number increases. Nobelium is extremely unstable and has a half-life of only 3 seconds. The names are derived directly from the atomic number using roots for 3 digits in the atomic number of the elements and adding the EM. The roots for the number and their abbreviations are. In some cases, the names are shortened by removing the repetitive letter. Plus EM can be written as BM or EM can be written in the short form as TM. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of the element is derived by combining together the roots in the order of digits which make up the atomic number followed by adding EM in the end. Nomenclature elements with atomic number above 100. Look at this table. No IUPAC name has yet not been announced. Elements not yet discovered. Comparison of actinides and lanthanides. Both lanthanides and actinides constitute elements of F block as these involve the gradual filling of F orbital. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties but also differ in many properties. Let us review some of the important points of similarities and differences among the lanthanides and the actinides. Both the lanthanides and actinides involving the filling of F orbitals. Both the lanthanides and actinides display predominantly the +3 oxidation state in most of their compounds. Due to poor shielding of 4f and 5f electrons, both lanthanides and actinides show gradual contraction in the size of their atoms with the increase in atomic number known as lanthanide and actinide contraction respectively. Elements of lanthanide and actinides with the same number of unpaired electrons display similar absorption spectra due to FF transition. Lanthanides and actinides are highly electropositive and are very reactive. Nitrates, sulfates, and perchlorates of trivalent lanthanides and actinides are soluble in water. Hydroxides, fluorides are carbonates of trivalent lanthanides and actinides are insoluble of water. Both lanthanides and actinides can be separated by ion change method. Point of differences. The important points of differences between the lanthanides and actinides are present in the table. Table 5.8. Difference between lanthanides and actinides. Serial number property lanthanides actinides. Metal orbitals. It involves filling of 4f orbitals. It involves filling of 5f orbitals. Energy gap between f and d orbital. The energy gap between 4f and 5d orbitals in lanthanides is very large. As a result, their chemistry is fairly similar. The energy gap between 5f and 6d in actinides is small. As a result, their chemistry is very different. Binding energies. Binding energies of 4f orbitals are higher in lanthanides. Binding energies of 5f orbitals are lower in actinides. Oxidation state. The most common oxidation state is +3 in addition to some lanthanides showing +2 and +4. The common oxidation state is +3, addition to some actinides showing +2, +4, +5 and +6. Shielding effect. 4f electrons exert great shielding effect, 5f electrons exert poor shielding effect. Ability to form oxocation. Lanthanides do not form oxocation. Actinides form oxocation is higher oxidation states. Colors of the ions. Most of the lanthanides ions are colorless. Most of the actinide ions are colored. Complexing ability. The tendency to form complexes is small. The tendency to form complexes is large. They do not form complexes with bonding ligands. Radioactivity. All lanthanides except promethium are not radioactive. All the actinides are radioactive. Coordination number. Lanthanide display coordination number 6, 7, 8 and 9. Actinides display higher coordination number 8, 9 and 12. Basic character. Components of lanthanides are less basic in character. Compounds of actinides are more compounds of actinides are more basic in character.